Now, in this video, we'll be talking about the laws of photoelectric effect. Basically, these are the statements that we conclude from the previous video where we had the experimental uh, the experimental approach to study photoelectric effect. Now, for each emitting surface, there is certain minimum frequency. We have seen that we couldn't find any photoelectric effect unless the radiation has some minimum frequency greater than that of some fundamental frequency, and that fundamental frequency is different for different materials, and we call that frequency as threshold frequency, and we represent that by symbol nu naught. And below this frequency, whatever the conditions are, whatever the voltages are, whatever the radiation that you will use off, if its frequency is less than that of this threshold frequency, there is nothing like there is no electron coming out of this uh, out of that metal. The next important point is that for the given frequency, which is to be nu greater than nu naught, the number of photoelectrons emitted per second for a given surface under a constant accelerating potential is directly proportional to the intensity of light. Okay, that can be set as a law of photoelectric effect that we saw, that we observed when we had a graph between photoelectric current and intensity of light. But what was important for that, this intensity of light is directly proportional to the photocurrent. But the necessary condition for this relation between intensity of light and photocurrent is that this frequency has to be greater than that of this minimum frequency. Then this photoelectric emission is almost instantaneous. It's instantaneous. And what does that mean? That means that the emission takes place in a time less than that of 3 into 10 to the power of minus 9 seconds. Even when the intensity of the incident light is as low as 10 to the power of minus 10 watt per meter square. So this photoelectric emission is instantaneous. So you have the light falling on it instantaneously. You have an electron coming out of the surface of this metal, and the time that it takes is in nanoscale, very instantaneous. The next important that can be attributed as the law for this particular experiment that has been conducted for different materials, the maximum kinetic energy and hence the maximum velocity of this ejected electron, it increases with the increase in the frequency of the incident light. So this is the important point, that as you go on increasing this frequency, this increases the kinetic energy, and hence we have a corresponding electron having maximum kinetic energy. And what is important here is that that the light incident that's incident on this photosensitive metal has a frequency greater than that of this threshold frequency. So that's the necessary condition. And this maximum kinetic energy or the maximum velocity is independent of intensity of light. So all you have to do with the kinetic energy of the ejected electron or the velocity of the ejected electron is totally dependent on the frequency, and it does not have any dependence on the intensity of the radiations. The next important point is that the stopping potential that we discussed in detail, and as we try to to have that stopping potential, this stopping potential that was already defined, this stopping potential for a given metal surface is proportional to the frequency of the incident light. But this stopping potential is independent. It's independent of intensity of light. So if you increase the intensity of light, if you increase the number of the photons, there is no effect on the stopping potential. It was explained in the previous video because the energy of all the electrons is same. So the stopping potential for all the electrons is same, even though their intensities are different. Now the point is, so this is the set of five statements that I have talked about. These are the observations that we have tried to articulate in those sentences regarding this photoelectric effect. Now, what comes next is the failure. It is the failure of classical physics. It's the failure of electromagnetism in general. Electromagnetism, classical electromagnetism, which is based on classical laws of physics, Newtonian laws of physics. So now let us discuss those. Let's talk about those the inadequacies that the classical theory has to explain what we have observed in photoelectric effect experiment. So long, according to this electromagnetic theory, according to the classical electromagnetic theory of light, a substance that's exposed to light is subjected to an oscillatory electric field. It's an electromagnetic wave. An electric field is oscillating. It has an oscillating component of electric field and magnetic field. And the intensity of light being proportional to the square of this amplitude. It is proportional to the square of this amplitude, and I think electric vector is taken as the amplitude, or in general we can take the amplitude of this electromagnetic wave. So this intensity is proportional to the square of the amplitude of this electric field vector. And the electrons within the substance, we have a substance, we have electrons, they interact with the field, and they certainly gain kinetic energy and leave the substance as soon as the kinetic energy exceeds the binding energy of these electrons with respect to their atoms in a lattice. The electromagnetic energy that's gained by this electron, it depends on intensity. It depends on area of surface over which this light is falling, and it depends on the exposure, the area of exposure. That's also important. Area of exposure to the light. And time. Time is another important point, that for how long the light is falling on this material. So this is classical way of looking at it. Now, taking into consideration these things, if we consider that the light falling on a sodium surface, suppose we have a surface of sodium, and a detachable photoelectric current will be obtained when we have when we have a power of 10 to the power of minus 6 watt per meter square of electromagnetic energy that we are applying on this on this on this sodium plate. So what we have sodium plate, right? And we have a sodium surface, and its surface can absorb the electromagnetic energy, and a layer of this sodium, say one atomic energy, is absorbed by this surface, right? And what we expect, we take 1 meter square of the area, and it has nearly 10 to the power of 19 atoms of sodium in it. Now, if we suppose that the incident light is absorbed by the uppermost layer, so there are layers, the light is absorbed by the uppermost layer of sodium atoms. Each atom will receive an average amount of energy, and that average amount of energy will boil down to 10 to the power of minus 25 watts. Right? So that the atoms, each atom will receive this much of energy. And so that 1.6 to the power of 6 seconds for this moment of time, if I take this as a limiting case, nearly 2 to 3 weeks. This much of time will be required if you have this much of energy that's being absorbed by one sodium atom on the top layer of this material. This electron will come out of the sodium atom on the top surface of this material by the amount of energy that will be absorbed by a single atom in an area of 1 meter square, which has nearly 10 to the power of 19 atoms in it. So to have this much of energy, which is nearly 1 electron volt, and an electron in sodium will gain sufficient energy to be liberated to get it out from this metal surface. It will take him 2 months nearly to come out of this metallic surface. So taking this crude example into consideration, which is based on the electromagnetic theory, the classical electromagnetic theory, where we have taken into account the intensity, taken into the account the area of surface, the area of exposure, and time. Applying all of these points to a given problem indicates that the electron will take 2 months to get out of this metal surface. So this is a failure. Hence, the electromagnetic theory fails to explain why there is no time lag between the instant the light falls and that of the emission of the photoelectron that we have observed in the experiments. Now, secondly, according to the classical electromagnetic theory, the ejection of an electron, it should depend upon the incident energy. And what is energy? What is the incident energy in classical electromagnetic theory? The intensity of the light, and it should not depend on the frequency. Yeah. And what does it mean? There should be no threshold frequency at all. There should not be any threshold frequency for any material. And this is a contradiction to what we have observed, and we have repeatedly seen observed in the experiments that we don't have any photoelectric current. We don't have any photoelectric current. If this threshold frequency is less than, if the frequency of the incident light is less than that of some threshold frequency. Again, there is no limit on the maximum energy to be transferred to the electrons. The electrons can have any value of maximum energy. This is also contrary to what we are observing from the experiments, the experiment that we have performed. So hence, we would say that this electromagnetic theory of light fails to explain the basic facts of this photoelectric emission, and the very fundamental fact is this frequency, which we see that the emission is dependent on this frequency. If this frequency is less than this threshold frequency, there is no photoelectric current. Even if the intensity of the light that we understand from a classical electromagnetic theory point of view, which depends on intensity, which depends on area of exposure, which depends on time, that doesn't work. There is no photoelectric effect for this condition. But if this condition is like this, then we have the photoelectric effect. And the arguments of classical electromagnetic theory in terms of intensity of light, they are also fulfilled here, where we find a correlation between the photoelectric current and intensity. It shows a proportional behavior. But the condition is that this nu has to be greater than nu naught.